All right, welcome to Unit 2, Exploring Two Variable Data. This is AP Statistics, and we're going to cover topic 2.4, representing the relationship between two quantitative variables. So now that we're done with categorical variables, we're going to move on to looking at the relationship between two quantitative variables. So what are we going to learn here? In this topic, we will explore the relationship between two quantitative variables, can't say that enough, measured from the same individual to discover if there is, in fact, relationship between those variables. So it's important here that we're not just gathering two random sets of quantitative data, ages from a group of kids in California and then heights from a group of kids in Ohio. No, we're going to take one kid and we're going to measure two quantitative variables from that one individual. And then we're going to get another kid and measure those same two quantitative variables. And then we're going to get another kid. Or maybe we get a horse and we measure two quantitative variables from that horse, height and weight. And then we get another horse, two quantitative variables, height and weight from that horse. So it's important that you understand is that we're going to create data points. And each point represents an individual. And we're going to measure two data points on that individual, a quantitative variable and a second quantitative variable. And the goal is to see if there's any kind of relationship between those two variables. So this is known as bivariate quantitative data. Bivariate. Prefix bi means two, right? So a bivariate quantitative data set consists of observations, data, of two different quantitative variables taken from individuals in a sample or a population. So the key here is that there's two quantitative variables measured from the same individuals. Have I repeated that enough? I hope so, because it's an important point that a lot of kids mess up. So here's an example. Get 30 students and measure each person's height and weight. So I'm going to have 30 data points. Every data point is going to have a height and a weight. Get 30 menu items from Burger King and measure each item's protein content and fat content. So I'm going to have 30 data points. Each data point is going to be, an item from Burger King, a Whopper, for example, how much protein's in that Whopper, how much fat's in that Whopper. All right, what does bivariate data look like? Well, this means each individual has two values, which we can turn into a point. X for the first value, Y for the second value. Each individual's point can be plotted on an XY coordinate grid to create what we call a scatter plot. So if you've ever heard of a scatter plot before, it's exactly what we're talking about. The collection of all the points is a scatter plot of the data. Scatter plots are the only way to display the relationship between two quantitative variables. Again, we're not comparing heights from this group of kids versus heights from this group of kids. If we were just comparing, we'd use box plots, histograms, stem and leaf plots. But we're not comparing. We're looking for relationships. That's a big difference, right? We're trying to determine, does X have any relationship to Y? But the question is, all right, so I have this data point. X is one of the variables. Y is the other variable. But which is the X and which is the Y? Well, here are the two variables that we are going to define. The explanatory variable is the variable whose values explain or predict a response variable. This is the X. Think explanatory. It's really kind of hard to mess that up. Explanatory is the X variable. Now, the response variable is the variable that gets impacted by or influenced due to the explanatory variable. So when you're reading the problem, you want to identify what variable do I think is impacting the other variable, right? And the one that's doing the impacting, the one that's doing the explaining, that's the explanatory variable. It explains the response, right? So if we think of the point X comma Y here, the X variable explains the Y variable, and the Y variable is responding to that X variable. So most problems have a clear explanatory variable that is clearly impacting the response variable. But if it seems unclear to you, just look at the scatter plot, right? Because the explanatory variable is always going to be on the x-axis, and the response variable is always going to be on the y-axis. So even if, just reading the two variables, you're like a little unsure which one's doing the explaining, which one's doing the responding, just look at your scatter plot, and you'll clearly see that the x-axis has the explanatory variable. You can't mess that up. And the y response variable is on the y-axis. All right. Please understand that the explanatory variable accounts for changes in the response variable, right? Avoid using the word cause. It's actually hard for me to avoid using it, but I really have to take my time to avoid using it. it's hard to ever say that one variable causes another variable. We may think that that's pretty obvious. We may feel that that's really true. It might be our gut instinct, but we don't ever really want to use the word cause because it's so hard in the world we live in where there's so many variables at play to say, if you drink milk, it's going to cause you to get taller. The more milk you consume, that's an explanatory variable, it's going to cause you to get taller. That would be the response variable. But boy, I mean, there's a lot of other things like genetics, exercise, mom's height, dad's height, how much food you eat. I mean, there's a lot of other things that go into how tall you are besides just drinking milk, right? So that's why we don't like to use the word cause. We use like kind of vague things like explains or impacts or accounts for changes. Like milk might account for changes in height, but it's not actually causing. So please avoid the word cause. All right, here's some examples, right? How does the amount of college debt impact a person's stress? If you measure stress on a scale of 1 to 10, then it does become quantitative. So I would assume that the more college debt somebody has might lead, not cause, might lead to more stress. How does the amount of sleep impact a test score? If I get a lot of sleep, I'm well rested, I feel good, I might do better on my test. How does a person's height impact their weight? Well, if I'm taller, then I may just happen to weigh more because I got more body there. You know what I mean? Who knows? How does the size of a pitcher's hand impact the speed he could throw a baseball or she? Well, if I got a bigger hand, maybe I could grip it more. And bigger hand might mean that I'm stronger. So maybe I have a bigger biceps, which means I could throw it faster. Who knows? How does the amount of alcohol in the body impact the body's temperature? So both of those are quantitative variables. If I have more alcohol in my body, does that make the body warmer? Overall temperature. And again, the cool thing about all these things is the reason why we don't use the word cause is because there can always be something that doesn't fit. Like there can always be a short person who weighs a lot. There can also be a person who got a half an hour of sleep but got 100% on the test. Or there could be somebody who has a tremendous amount of college debt, but they have no stress. So, I mean, that's why we don't like to use the word cause. We like to look for relationships over large sets of data. All right, so let's actually get to an example here. So here's an example of a scatter plot, right? You see a bunch of points, and let's read what this problem's all about. I spelled that wrong, geez. An ice cream store looked at 12 days. On each day, they record the max temperature for that day and the amount of money they made in selling ice cream that day. Do you see any kind of relationship? So what we looked at here was an X value on this chart would be the temperature, right? That would be the X on that day. And the Y value would be the sales of ice cream for that day. So for example, on this day right here, looks like the temperature was, I got to estimate maybe 14.2 degrees and Celsius. And we sold, again, I got to kind of guess here, maybe $210 of ice cream. And each point represents a day. And again, that day was measured twice. We measured the temperature of that day and the sales of that day, both quantitative variables. So now we see a pattern, right? I see a relationship. It appears that if it's warmer outside, the store sells more ice cream. Kind of makes like a lot of sense. So that's what we're looking for is, 1 point isn't going to tell you anything, right? But over several points plotted, we might see a pattern. Now, does this mean that literally when the temperature goes up, it's literally going to put money into the cash register? Well, no, obviously that's not a cause relationship. There's other things at play, right? And this also means that, maybe you have a really warm day, but it rains a lot, so nobody feels like going to get ice cream. So you don't always fit the pattern. We're looking for overall relationships. All right, here's another one where we examined several students in a large college class that covered one full semester. We measured how many days each student was absent and what each student's final exam score was. Do you see any kind of relationship? So again, what's the explanatory? Number of classes missed. So the X value for each point is how many classes did you miss that semester? And the Y value, the response variable, was your final exam score. So for example, this person right here missed 10 days throughout the whole semester and got, and again, this is the tough thing, you're going to have to estimate maybe a 55 On the exam, who knows? It's kind of not very good. But the nice thing is once you have all these points laid out, you could say, hey, do I notice any kind of relationship? Do I notice any kind of pattern going on? And it's not perfect by any means, but it does appear that if you miss more days of class, you tended to have a lower exam score, okay? Now, there could always be an exemption, like, for example, this kid right here missed 21 days of school. That's kind of a lot, but he still did fairly decent on the test. So, don't always think that there's that cause and effect relationship. That's why we do not use that word cause. But we're just looking for kind of overall patterns that we may see in our scatter plot. All right, here's another one. A third scatter plot below shows data collected from a number of house fires in New York City. For each fire, we measured how many firefighters were at the scene of the first and at the scene of the fire. Man, a lot of typos. I apologize. And how much damage was done by the fire measured in dollars. So again, what we did here was we looked at the exponential variable of how many firefighters were on the scene. And then we looked at how much damage was done, and that was done in dollar amount. I guess maybe we need an insurance company to kind of figure that out for us. So again, for example, right here, this particular house that caught on fire had about 11 or 12, hard to say, about 11 firefighters. And they had, this is $500,000. Maybe this is $100,000 worth of damage. Now, these numbers are quite big, right? This is $1 million. Well, if you've ever been to New York, houses in New York cost a lot of money. So maybe that's why so much damage if a house burns down a lot. So overall, we do see a pattern here, and it's a little bit of a shaky pattern. It's not the clearest of patterns, but it does appear at first glance that if there's a lot of firefighters at a scene, then there's going to be more damage, higher amount of damage. Now, does that mean firefighters cause damage? No, the fire causes the damage, but if there's a really big fire, you're going to need a lot of firefighters, but if there's a really big fire, you're going to have a lot of damage. So the point is that there's always other variables at play, like how big the fire was, how long the fire burned for, but all we're looking at is two variables here, and we're just looking for a pattern or relationship in those. Again, don't use the word cause. So this is really important that you understand. This is bivariate data, right? Scatterplots, bivariate data. A single house measured how many firefighters were there to put out the fire, how much money, right? Bivariate data is not just looking at two random groups of people and looking at two random quantitative variables. So please keep that in mind. All right, so when you describe a scatter plot, when you look at a scatter plot, you got to be able to talk about it, right? And there are 4 characteristics of a scatter plot that must be used anytime you're asked to describe one. And you better believe on quizzes and tests, I'm going to give you a scatter plot. I'm going to say, hey, tell me what you see. And these 4 things have to be addressed: direction, form, strength, and I want to know what the pattern is in context. So let's talk about what each of these things is a little bit more specifically. First, direction. Direction is literally just positive or negative. Like overall, do you see a positive trend left to right, or do you see a negative trend left to right? We always read graphs left to right. So we always look at the explanatory variable going up. And then the question is, what's happening to the y variable, the response? So as the size of a diamond in carats goes up, we see that the price goes up. That is a positive direction, very clear. Over here, we see as the number of drinks goes up, the score on a dexterity test goes down. A dexterity test is like solving a puzzle with your fingers, right? Something where you're using your hands to solve a puzzle. Some type of test where you're using your hands. So if people have more drinks, they might get more drunk, and that causes them to not do so well with using their hands to solve a puzzle. So again, you always look at the x's going up, and then you ask yourself, what's the y doing? In this case, it's clearly negative, okay? So direction is actually really, really easy. Nobody really struggles with that. You're just looking, is the data going up? Is the data going down? All right, then we look at the form. Form is what overall shape are the points forming? If there is any form, it can be described as linear or nonlinear. And nonlinear could have varying degrees. Like you could see a giant curve or a slow curve or a parabolic curve. So we usually just kind of separate it as, do you see a line or do you see anything other than a line, which we just call nonlinear? So make sure you really explain in context, and we're going to talk about that in a minute, what this means for your data. But, in this first graph, You might not see a perfect line, but we do see kind of an overall linear pattern here that is clearly negative, right? In this middle one, we see a slight curve. So that's like nonlinear, and it's just slightly nonlinear, like a slight curve. And then here we see a parabolic curve. This is clearly not linear. It's a clear curve that starts going down and then continues going up afterwards. So, look for the form. We're usually just classified as linear if we see a line, or nonlinear if we don't. All right, third is strength. The strength of a relationship in a scatter plot is determined by how closely the points follow a specific pattern or form. So if you can clearly see a straight line, it's probably going to be pretty strong. If you can't even tell if it's a line, well, I'm pretty sure that would be what we call weak. This is very vague right now. We'll get a little bit more specific later. But really, we're just looking at if the first two topics were direction and form. So if the direction and form are very easy for you to see, positive, linear, well, then it's probably pretty strong. If you're like, man, I can't even tell if those dots are going up or down, it looks like a swarm of bees, it doesn't even look like a line, then that would be pretty weak. So here are some examples. This one is going to be very strong, right? Very strong linear, very, very strong. The dots form a very clear pattern. That's a strong strength. This one is like, weak, moderately weak. You can even say, like, I definitely see a pattern forming. I definitely see positive, but it's not clearly forming a line, so that's like maybe moderately strong. Here we literally have nothing. Like, I can't even tell if the dots are going up or going down. It's just a giant swarm of bees. There's clearly no line there. That's going to be extremely weak in terms of strength. And then here we have a non-linear relationship. We do see a clear curve. So like the curve itself is kind of strong, but it's definitely non-linear. So strength is a little bit vague right now. We're just kind of saying, hey, if you see a form, how strong is that form? How close to the points make that form that you see? All right, now the last thing you have to have, and for some reason I can't believe how many students forget this, is an overall description in context. So the final item should include a description of your scatter plot in context. For example, I notice in a scatter plot that as the height of a person increases, the size of their hand tends to increase. Okay, avoid using the word cause. I already said that several times. But again, if the question deals with height and size of their hand, then I clearly want to incorporate that in my answer. Always lead with the explanatory. Remember, the explanatory is always going up. So I say, as the explanatory variable is going up, the response variable is going, and you just fill in the blanks. But add that context in. Don't forget units, and don't forget the actual words of the problem. So when you look at a scatter plot, I want you to talk to me about direction, form, and strength, which you can actually usually do in one sentence. Like, hey, that scatter plot looks positive, pretty linear, and very strong, right? So you could do that in one sentence, and then give me that final sentence that gives me what is happening in context. So let's go ahead and practice this, right? So here what we looked at is we studied several years. So the individuals, each dot represents a year. And each year we looked at how many boats were registered in Florida and how many manatees got killed that year. Manatees are huge, very nice, lazy sea animals. And they tend to kind of hang out by boats. And if the boat's propellers get turned on, then they could kind of get injured and maybe die. So what we notice here is that each dot, the explanatory variable, is how many boats are registered in Florida. And the Y variable, the response variable, is how many manatees got killed. And, if I'm describing this, I'm probably going to say one really quick sentence. I see a positive, linear, very strong relationship. Then I want to give that last comment about what I see in context. And it does appear that as the number of boats registered in Florida goes up each year, there's a tendency for the number of manatees to get killed each year to go up as well. Don't use the word cause, right? Just talk about tendencies, overall patterns, but don't use that word cause. So again, describing scatter plots is actually really, really simple. It usually only takes like 2 sentences. Just really take the time to make sure they're written really, really well. And that's it for this video. In the next video, though, there's going to be a quick video over how to make your own scatter plots. It's nice when they're made for you. I mean, you don't have to do any work, but we do need to know how to make them on our own. So we'll check that out in another video. But this is important to understand what it takes to describe a scatter plot.